Hey, Chem 20s, Chem 20 IBs. Round 2 of structural diagrams. All right, let's review. How many lines does hydrogen get? 1. How many lines does sulfur get? 2. How do I know this? Well, I've memorized it because I'm a giant nerd. Also, the number of lines you get in a structural diagram coincides with the number of electrons that can bond. So if I do the Lewis diagram for sulfur, sulfur has six electrons. There are 2 bonding electrons. That coincides with 2 areas that it can bond. So that's how you know, or you can memorize it. Set it up symmetrically. Hydrogen gets 1 line, sulfur gets 2. Good to go. All right, carbon dioxide, CO2. All right, let's set this up symmetrically. How many lines does oxygen get? 2. How many lines does carbon get? 4. Oh, now each oxygen has 2, and the carbon in the middle has 4. All right. Now, when we get down to ions, polyatomic ions, it's really tough to go to structural diagrams because the bonding rules don't matter, or they don't work. So you're going to have to add up valence. So iodine's in group 7, so there's 7 valence. It's got 7 valence electrons. Oxygen has 6 each, so that's 18. There's 3 of them. 6 times 3 is 18. And then it's -1, so we add an extra electron. So what does that give us? That gives us 26 electrons total we can use. All right. In polyatomics, usually the ion or the atom that has the least amount is our central. So we'll put the iodine in the middle and try and make it symmetrical. Okay, hook up your central to peripheral. We've got 20 left. What do we do with those 20? We put them around the outside. 6, 8, 10, 12, 14. Whoa, what did I do here? Sorry. So we got 2, 4, 6. That's right. So 2, 4, 6, 8, 10, 12, 14, 16, 18. There we go. I was counting wrong. So I've got 2 electrons left. Where do they go? They go on the top. Okay. Then turning this into the structural diagram, every line is represented by a single bond pair. So our structural diagram looks like this. Pow! Okay, so that's a quick review of structural diagrams. Now, the other thing I had a student ask was, how do you know what the central atom is? Okay, so I've mentioned this before, but I'm going to mention it again. Let's say we had this mess. It's probably not going to work as like actually trying to make it as a compound. But how do you know which of those is our central atom? Well, we've got acetone, nitrogen, oxygen, and hydrogen. Now, which 2 of these absolutely can't be the central atom unless it's in a polyatomic, but this is not. And the answer is hydrogen can't. Hydrogen can only bond to one thing, so you can't have hydrogen in the middle bound to all this other crap, right? That doesn't work that way. Okay. Acetone only has 1 bonding electron because it's a halogen. It only is allowed 1 stick to it. So now it's between nitrogen and oxygen. If you're unsure, the central atom is always the atom that has the most bonding electrons. Nitrogen's single Lewis has 3. Oxygen with 6 electrons has 2. So what's the central atom? It's nitrogen. Okay, this is a little bit of an IB concept, so regulars, you can listen along. I'm just giving IBs a heads up that this comes next year. There's something in chemistry when you draw Lewis diagrams and structural diagrams called resonance. And it's a way that you can draw more complicated molecules in different combinations and still be correct. Now, I'm only going to show one of these because it is kind of confusing, but you'll see what I'm getting at. So the nitrate ion is a good example of that. So nitrogen has 5 valence, oxygen has 6, so that's 12 plus 1 gives me 18 electrons total to deal with the nitrate ion. Okay, let's set it up symmetrically. Link it up 1, 2, 3, 4, and then put our peripheral in 6, 8, 10, 12, 14, 16, 18. Okay, now problem if we look at this is that we don't have 8 electrons around the nitrogen. So if you remember from previous lesson, we can borrow. Now, if I was to redraw this with it borrowed, I would get something that kind of looks like this. In advanced chemistry, where there is a single bond, it's more negative. So that's where the negative would be. It'd be more on that side. Mr. Zelensky in the next level of IB, what might explain that? Now, the question becomes, we've talked about this before. I could have borrowed those electrons from the other side, right? There's nothing stopping me to saying, you know what, to make this work, I could have borrowed those electrons from here. And that is correct. So you could also have written it to look like this. That is correct. Both of those are fine. Now, in regular chemistry, the regular chemistry teachers just mark whatever as being correct. Okay, so if it didn't matter which way you drew it, it's technically correct. In higher level chemistry, you have to show every possibility sometimes. You have to show something called resonance structures. And when we draw the structural diagram of this for regular chemistry people, you might just go like this, right? Oh, I should have put brackets around this, right? It's negative. Negative, so this is negative. So that's what it might look like. Now, because both of these are equal to each other, right? It's just basically drawing of the same molecule. If we were to draw this, this is what it would look like. You'll have a dotted line. Maybe you've seen that on the internet before, but that shows that when in nature, it's an average of a double bond on one side and a single bond on the other. It's almost like it's a 1.5 bond. That's a resonance structure. Now, you're not going to be tested on it this year. Regular chemistry people, if you tuned out, whatever. I'm just showing you so you've seen it before. Okay. Now, the next part of this lesson takes our structural diagrams and turns them into something called a stereochemical shape, an actual 3D shape that exists in nature. Now, sadly, this is a really fun part because we break out the model kits and everybody's making molecules with our little model kits. So I'm going to shoot a video that will follow this, that will show all the different shapes. I'm going to build them and you can see the different shapes. I'm going to go over the theory today. So this is a kind of a heady lesson. So if you get bored and you want to shut her down, you can shut her down in a bit. I'm going to go over all of the different shapes. Okay, so there's a lot to this part of the unit. This is a 2-day unit, but I kind of didn't work for me to have this as, okay. So I'm going to start with the first shape, and that's a shape made from carbon and silicon and any central atom surrounded by 4 substances. This shape is called a tetrahedral. Okay, it's called the tetrahedral. Your central atom has 4 bond pairs. So if I turn methane, CH4, into the Lewis diagram, this is what it would look like. So when your central atom is surrounded by 4 things, or it has 4 bond pairs and 0 lone pairs, it turns into a tetrahedral molecule. Now, we've covered the structural diagrams, and you're going to be kind of annoyed with me. The structural diagrams are great. But remember, these molecules exist in 3D space. That is a flat picture. What this molecule looks like in 3D space looks like this. You have your central atom, and depending on how you turn it, one of the bonds is represented by a triangle bond to show that it's coming out at you. Another is in the same plane of the paper. The next one is shown with a dotted line because it's actually going into the paper. Like if you're drawing this flat, it's going away from your frame of reference. And the last one is shown like that. Okay. Now, for IB students, you have to memorize the bond angle. So there is an angle that exists for tetrahedral molecules that's 109.5 degrees. Okay. Okay, so again, that's what it looks like. So when you're asked to draw a stereochemical shape, you have to be very careful. It's not a structural shape. Okay, it's a 3D shape. And the tetrahedral is the easiest one to wrap your head around because tetra means 4. Anything in carbon's family, like carbon and silicon, if silicon was surrounded by 4 things, and it doesn't matter what 4 things it is. In fact, it could be surrounded by 4 different things. Like let's say we had hydrogen, chlorine, fluorine, and bromine. The silicon is a tetrahedral because it has 4 bond pairs. So we would have to show that one line is going away, one is in the same plane, and one is in the same plane again, and one is going at you. Now, other things that are tetrahedrals are anything else where the central atom is surrounded by 4 things. So a polyatomic solves it for you. There's no other way and no other shape for this. If phosphorus is your center, you can jump straight to, oh, I screwed that up. You can jump straight to the stereochemical shape because there's no other shape it could possibly be. The central atom has 4 things around it. Okay, that's shape number 1. Shape number 2, a central atom with 3 things around it. This is called pyramidal or pyramidal. What makes this different when we look at the Lewis dot diagram is it now has a lone pair. So the pattern for this one is 3 bond pairs and 1 lone pair. This lone pair of electrons, because it's not attracted to anything, is very loose. It gets fuzzy and it takes up way more space. So those little dots, those little packets of energy, they spread out and they become giant, huge negative repulsion zones. That's why the start of this was valence shell electron pair repulsion theory. Those valence electrons are actually going to shove the hydrogens down. So what does this diagram look like? Well, we have a nitrogen in the middle. One of those hydrogens is coming out of the page at us. One is in the same plane as the page, and the other, is going away from us. Okay. Now, because those 2 giant electrons are cramming them closer together, our bond angle shrinks. And our bond angle now is 107 degrees. So IBs, you have to remember that. Everything in nitrogen's family, nitrogen, phosphorus, arsenic, anything surrounded by, well, this is a little bit of a caveat here. So if you have nitrogen and it's got lone pairs, it's going to be that pyramidal shape. So that's shape number 2. Okay. Now what happens if you have a central atom with 2 things around it and 2 lone pairs? So for example, if I was to draw oxygen, it would look, or water, it would look like this. So the central atom has 2 bond pairs and 2 lone pairs. This is the most creatively named shape in the history of shapes. It's called angular and sometimes called bent because those electrons bend it even further. Our central atom has 2 bond pairs and 2 lone pairs. So those electrons that aren't bound to anything, they take up a huge amount of space. And because it's only got 2 things attached to it, there is no fancy triangle line, no fancy dotted line. It's in the same plane of the page. And our angle shrinks even more to 104 degrees or 104.5 degrees. That's shape number 3. That's shape number 3. anything that looks like oxygen with two things around it in the same family is also a bent shape. So H2, SeF2. Those are all bent or angular molecules. Now, this might be a good place to take a brain break and shut her down. If you want, I'm going to actually, you know what? That's a good idea. Let's just stop right here. And tomorrow I'll pick up with the last two shapes because they're a lot more challenging. They are the trigonal planars and the linear molecules. Okay, so just a quick recap before we shut her down. The three shapes we went over are tetrahedrals, pyramidals, and angular or bent molecules. Carbon with four things around it is usually tetrahedral. Nitrogen with three things around it is a pyramid. Oxygen with two things around, or oxygen like OH2 or OF2, oxygen with two things around is angular. The only two shapes that have the crazy dotted and triangle lines are tetrahedral and pyramidal. So the next two shapes, shape 4 and 5, I'm going to talk about tomorrow, they don't have those crazy shapes. It's only tetrahedral and pyramidal. Okay, so that's a good time to take a break for today. You have enough stuff to keep working on the assignment. All right, we'll talk tomorrow.